Hello! In this video, we are going to prove the following theorem. The arctangent of negative x is equal to the negative of arctangent of x for all real numbers x. So we're essentially proving that the arctangent function is an odd function. Now, first of all, let's remind ourselves of our definition of the arctangent function. Let x be any real number and consider the following sequence. So when I say for all n, I really mean for all integers n greater than or equal to 0. This is just shorthand for that. And so we can think of this sequence as the sequence generated by x. Well, it turns out we have previously shown that the sequence 2 to the n xn converges. And we defined the value it converges to be the arctangent of x. Okay, so now let's get into proving this theorem. And since we're trying to prove a statement about every real number, let's give ourselves an arbitrary real number x. And from here, we are going to consider the sequence generated by x and the sequence generated by negative x. We define those sequences as follows. Now, by definition, the limit of 2 to the n xn is equal to the arctangent of x. And the limit of 2 to the n yn is equal to arctangent of negative x. And we want to show that these two guys are negatives of each other. To show that, what would be nice is if we could show that yn is equal to the negative of xn for all n. And we're going to prove this by induction. Now notice, the base case is pretty easy because by definition, y0 is the negative x, and x0 by definition is x, so negative x is negative x0. So we have y0 is equal to negative x0, so the base case is done. So for the induction step, we suppose inductively that yn is equal to the negative of xn for some n. And now we want to show that yn plus 1 is equal to the negative of xn plus 1. Well, yn plus 1 by definition is this. And since we're assuming that yn is equal to the negative of xn, we can replace the yns with negative xn. So we have this. But then, clearly, 1 plus negative xn squared is equal to 1 plus xn squared, and we can just pull the negative sign to the front of the fraction. So we have this. But, by definition, this guy is equal to xn plus 1. So this is just negative xn plus 1. So we have that yn plus 1 is equal to negative xn plus 1. So this closes the induction, and so our claim is proven. We have that yn is equal to negative xn for all n. And because yn is equal to the negative xn for all n, certainly 2 to the n times yn is equal to the negative of 2 to the n xn for all n. And now we can establish that these two guys are negatives of each other. First of all, we know that arctangent of negative x is equal to this. But remember, 2 to the n yn is equal to negative 2 to the n xn for all n. So certainly, the limit of 2 to the n yn is equal to the limit of negative 2 to the n xn. But we know from properties of limits, we can pull the negative sign out. And we know that the limit of 2 to the n xn is equal to arctangent of x. So this is just negative arctangent of x. And so we have that arctangent of negative x is equal to negative arctangent of x. And that is exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.